BKDS means BSV, key derivation scheme. So key derivation is what we're doing. So this, you could call this a primitive. So a primitive in the larger umbrella of BRC 100 even. And so we're going to talk about a few primitives that are involved in BKDS. First, we're going to talk about private public key pairs, and we're going to talk about ECDH, and we're going to talk about HMAC. Because all three of these are involved in ECC, as we're discussing here. So elliptic curve cryptography, and within the BKDS concept, how we're deriving keys. So you actually use all three of these primitives every day without even knowing it. So there's nothing revolutionary about the use of these primitives. It's how they're put together and for what purpose. And that might ring a bell with people that are deep in the Bitcoin study, because Satoshi designed the Bitcoin system based on a lot of parts. And he put them together in a unique and innovative way. So that's what's going on here too. So private public key pairs. So you need that before you even start key derivation. How you derive that is very important, but it's not the subject of this video. So ECDH is the next thing, and that is elliptic curve Diffie-Hellman. What this is a way to derive a shared secret with another party. So you've got party one and party two, without either knowing each other's private key. So together, you can each give each other your public key, and you derive the exact same shared secret. That's the simple way to talk about ECDH. So I won't go into kind of the math on all of that, but two parties, that is a departure. I'll take a second here. It's a departure from BIP 44, what we discussed in the last video, because BIP 44 doesn't care about the other party. It's just how do you derive your own keys, whereas BKDS presumes two parties, and we'll get to the why on that. Side note, you can still use BKDS even if you don't have a second party. I'm personally doing that with an application I'm developing, but we're going to work with the two parties because it's actually a really important reason for this whole scheme. So, all right, we just finished number 2, ECDH. You need the shared secret. And then number 3 is HMAC. So that's hash-based message authentication code. So HMAC, just described very simply, is you need a key, and you need a message, and you hash that message. And the output of that is called a digest. All right. So in BKDS, I'll explain how these work together. Because this shared secret here, this becomes the key. All right, so let's go to BKDS. So again, KD is we're deriving keys. You have a sender and you have a receiver, and it could be a simple payment. It could be lots of other things, and I'll get to that too. You have two parties. So each party has a private public key pair. Okay, and they exchange each other's public key, never private. They exchange each other's public key, and they do that ECDH thing, and they derive a shared secret. That shared secret is called an EC point. Then we go to the HMAC step. And this is where an innovation happens with the BKDS, because what they refer to something called an invoice number in that BRC, the BRC 42. Sorry about all these acronyms, but so when I set up here, key plus message gets you a digest once hashed. The key is this ECC point. So we've got our shared secret that we created together with our public keys, sender and receiver. And that is the key. And the next thing we need is a context. Why are we doing this? And that context in the BRC 42, they call an invoice number. But it doesn't have to be like a typical standard invoice/bill, right? It is a shared context. So I like to point that out in this world, because invoice number, it just makes your mind go to invoices, and it doesn't always have to be that way when you're deriving a key with this system. So I'll put context up here. Okay, so you take these two things and you hash them. I think it's SHA-256, yeah. And you get digest, which just means output. So we use the digest from the HMAC exercise we did, and we use it to create this scalar, just an integer. But that integer is used by the sender to tweak their own private key. Has to be the same key that we started with up here. So they tweak their own private key, and the receiver uses that same scalar to tweak their public key. Their public key. So the receiver's public key. And the tweaked result is a new public key that maps to the tweaked result of the sender's private key. So now we have a cryptographic anchor. And that cryptographic anchor is very secure. No private key was put on the internet ever. No shared secret was put on the internet ever. It's derived locally. And so you have something that can allow you to interact as a user, as a provider on the internet in a cryptographically secure way that we've never seen before. So let's review. So you start with your own private public key pair, right? And so does the user. So person one, person two, private public key pair. And then you trade public keys only. And then you create a shared secret using ECDH. Diffie-Hellman. You can read about that. It's just simple ECC math. Then you do HMAC, and the innovation in the BRC42 is the use of an invoice number, also known as a context, why you're doing something, why you're interacting on the internet. It might be an invoice. Maybe sender is going to pay an invoice. So the HMAC that's the hash-based message authentication code. We do HMAC on the shared secret that you created together. So your shared secret plus your shared context, so your invoice number, and you hash that with a hashing algorithm, and you get a digest. So the digest needs to be converted into an integer, which is called scalar. And that scalar is used to tweak our private key on the sender side and our public key on the receiver side. So you tweak with that scalar in ECC math to get a shared cryptographic anchor. So that's why there's two parties involved, and that's the innovation. All right, I wanted to share this table that goes through some of the implications of what this new model can get us. And these are just a few examples. So when you get API access, you typically go through the platform, you get the key, you register with them. All of that is gone with decentralized trust using BKDS. Secure messaging also. User and contact independently derive the same encryption key. It's not done for you like on Signal or WhatsApp or iMessage. You're the one in control of it. So it's truly peer-to-peer and end-to-end. Encrypted file drop. You don't need a Dropbox that holds it all for you and can look at it, and the voyeurism that happens with these platforms, that's gone. Cryptographic login, email and password sent to the server access gets decided there. Here you don't have the server. Login key is derived privately between two parties. And then, of course, the simple payment, which is the one that people are typically familiar with. On the internet today, user pays through a platform. The platform routes the funds to the recipient. With BKDS, there's a shared address derived, and it's only for the sender and recipient. So you can stop the video and look at this. It's pretty remarkable, all the things that can be done with this new
Got a curve in the game, laid out clean with the point named G and a math machine. Pick a secret number, that's your key. Multiply G, now the public can see. On the curve, can't fake what you sign. Private stays yours, public looking fine. No prime cracks, no factor spin. We keep it all locked with the number in. N sets the bounds, keep it in line. G walks the curve like it's right on time. Private jack gets G, that's the play. One-way trip, no backtrack way. ECDH sign, what's